This video is about oxidation and reduction. So the concept of this question is understanding the Winkler method. And we're going to use the explanation that comes in the question to explain the concept. So in the explanation, it tells us that the Winkler method is a type of redox titration. This gives us insight to what type of reactions that occur in the experiment using the Winkler method. It also tells us that it is used to determine the amount of dissolved oxygen in water. And that tells us the purpose of using the Winkler method. And that pretty much sums up the definition of the Winkler method. So we know that in our water sample, there is existing amount of oxygen in it, and it's our purpose to determine how much oxygen is in the water sample. So the first step of the experiment is adding manganese 2 sulfate and potassium hydroxide into our water sample. And so sulfate as well as potassium are spectator ions, and for that we don't need to worry about it or write it in our equation, so we can simplify it to Mn2 plus and OH negative. So the important reaction that occurs in this first step is manganese ion will be oxidized by oxygen and produce manganese oxide. From the first step, we get the chemical equation of 2Mn2 plus aqueous plus 4OH negative aqueous plus O2 aqueous makes 2MnO2 solid plus 2H2O liquid. For our second step, we're starting off with manganese oxide, which is the most important product from our first step. And from there, we add potassium iodide, hydrochloric acid, as well as starch. But for this example here, we don't need to worry about starch. So we have I negative and H plus. And the important reaction that occurs in the second step is iodine ion will react to form iodide, which is I2 aqueous. Chemical reaction we get from the second step is MnO2 solid plus 2I negative aqueous plus 4H plus aqueous makes Mn2 plus aqueous plus I2 aqueous plus 2H2O liquid. For our third step, we're starting off with the product from our second step, which is iodine. And there we will titrate it against sodium thiosulfate, which is S2O3 negative. The chemical equation that we get from the third step is 2S2O3 negative aqueous plus I2 aqueous makes S4O6 negative aqueous plus 2I negative aqueous. These three equations is our answer to our first question. And for the second part of our question is to find the concentration of oxygen. And so we already know the concentration and volume of our sodium thiosulfate solution. And from there, we can work backwards to find the concentration of oxygen. So we know that 2 thiosulfate ion reacts with 1 iodine molecule. And this is the molar ratio deduced from the third reaction. And so the iodine reactant in the third step is the same as the iodine product from the second step. From there, we can deduce another molar ratio of 1 iodine molecule to 1 magnesium oxide molecule in the second step of the chemical reaction. And the magnesium oxide reactant in the second step can give us the amount of magnesium oxide as the product in the first step. There we can deduce another molar ratio of 2 magnesium oxide to 1 oxygen, and that is from the first chemical reaction. The ratio between magnesium oxide and to iodine is 1:1, so we can substitute iodine in place of magnesium oxide, so we get 2 iodine to 1 oxygen. And then we also know that 2 thiosulfate ion is to 1 iodine, and we can substitute thiosulfate in the place of iodine, and we actually get 4 thiosulfate to 1 oxygen molecule. And so you can see how we went from our known concentration to oxygen concentration. And we can use this ratio to work out the concentration of oxygen. Going back to our question, we know that there's 50 centimeter cube of sodium thiosulfate solution, concentration of 0.005 mole over per decimeter cube. Starting out with what we know, we first need to change our unit from centimeter cube to decimeter cube, and we would get 0.05 decimeter cube. We need to find the number of moles to be able to use a molar ratio, so we take the concentration times the volume to get our number of moles, which is 2.5 times 10 to the power of -4. We know our ratio is 4:1, so we need to take the number of moles of thiosulfate, divide by 4 to get the number of moles of oxygen, and that gives us 6.25 times 10 to the power of -5 moles of oxygen. So going back to our question, we know that there's 100 centimeter cube of water sample. And again, we need to change the unit of our volume, so we get 0.1 decimeter cube. And to find concentration, we simply need to take the number of moles divided by the volume, and we get 6.25 times 10 to the power of -4 moles per decimeter cube of dissolved oxygen. And that is our answer for part 2 of the question.